Hello and welcome to the Sleepy Scientist. I'm really glad you found your way here. Maybe you're lying down, lights dimmed, wrapped in a blanket, or just a quiet moment. Maybe the hum of the day has faded, and the silence has a softness to it. Wherever you are, I've made this space for you. A gentle pocket of the night, where wonder and calm can sit side by side. Tonight, we're going to wander together, slowly, thoughtfully, into one of the universe's deepest mysteries. Black holes. Not in a rush, not in a textbook way, just as two people stargazing might wonder out loud, letting the dark sky pull their thoughts further and further out. Now, I should let you know I've done my best to make this story as sleepy and soothing as possible. But, well, black holes are just too fascinating sometimes. So, if your mind ends up wide awake with curiosity, don't worry. It'll drift off again eventually, a little wiser and a little more amazed. If you're already enjoying this quiet moment, I'd love it if you gave the video a gentle like, maybe even subscribe if you'd like more sleepy science stories. And if you're listening from somewhere special, a mountaintop, a little town, or just your favorite cozy chair, let me know in the comments. I love seeing the map of bedtime slowly light up. This video, like all others here, is for relaxation and education only. It's not a replacement for medical advice or professional sleep help, just a peaceful place to let your mind float. So now, let's begin. Lay back, take a slow breath, and look up. The night sky stretches out above you, vast and ancient, and full of questions. You can't hear it, but the stars humbly. You can't see it, but space is not empty. It's alive with gravity, movement, memory. The stars you see aren't just dots of light. They're messengers from the past. Their light has been traveling for years, decades, centuries, just to meet your eyes tonight. A star you see now may have died long ago, and yet here its light remains. A final letter from long ago, arriving late, but still full of meaning. And in between those stars, in the dark spaces where your eyes first see nothing, something else waits. Black holes. You won't see them. They don't send light your way. They don't sparkle or shine. They move silently, hiding in plain sight. But they are there, scattered like secret punctuation marks in the sentence of the universe. A black hole isn't a thing, exactly. It's a place where gravity is one. Imagine something so heavy, so compressed that even above a light, the fastest traveler in existence, though, cannot escape it. That's what a black hole is. Not a hole in the way we imagine holes in the ground, but a region of space where time and light and matter fall inward and nothing returns. They are born when stars die in very particular ways. Some stars, the largest ones, live fast and die with spectacular violence. When they've burned through all their fuel, they collapse under their own weight. Most stars become something gentler, a white dwarf or a neutron star. But if the star is massive enough, it collapses beyond all stopping, beyond atoms, beyond light, beyond time. And what remains? Not a fiery core or a glowing ember, but an absence, a silence wrapped in gravity. Right now, as you breathe slowly and deeply, there may be dozens, maybe hundreds of black holes silently drifting in our galaxy alone. They might have passed through whole star systems. They might be pulling on distant planets you'll never see. But what if I told you that sometimes black holes find each other? In the vastness of space, where things seem so still, black holes move, they drift, they circle, they orbit. And when two black holes come close enough, not quickly, not suddenly, but over millions, even billions of years, they begin to dance. At first, the dance is slow. Their immense gravity pulls them into orbit around each other. Like ghostly partners spinning in the dark, they spiral closer and closer, silently sending out invisible ripples. These ripples travel outward through the fabric of space itself, not as light, but as gravitational waves. You can imagine it like this. If space were a soft, stretched fabric, like silk pulled tight, then two black holes moving would tug and tremble that fabric. They'd send out pulses, small, stretching waves that carry the story of their motion across the universe. Those waves don't shake your body or your chair, but they are passing through you, maybe even now. If you could feel them, they'd be like the faintest heartbeat beneath all matter. Eventually, their orbit tightens and the black holes fall inward faster and faster until they merge, fusing into one larger black hole with a roar of energy that cannot be seen or heard, only felt in the silent stretch of spacetime. But we'll get to that. Tonight is about beginnings, about stillness, about lying beneath the sky and remembering that even in silence there are stories unfolding. And perhaps the most beautiful part of this story is how long it takes. Black holes don't rush. They move with the slowness of deep time, where 1,000 years is just the first note in a long, patient song. The universe is not in a hurry. And tonight, neither are you. So, as you drift, know this. Somewhere far away, two invisible giants may be circling each other in the dark. They are not fighting. They are not chasing. They are simply moving slowly, quietly, drawn together by something ancient and inevitable, a pull as old as the stars. You don't need to understand every detail to feel the poetry in that. Just breathe. Let your thoughts drift with them. Let your mind move like starlight, slow, weightless, and free. And as we rest in this quiet knowing, a new question forms, gentle, persistent, waiting just beyond the horizon of thought. What is a black hole, really? Let's float there next. So, what is a black hole, really? You've heard the name. Maybe it conjures an image, a swirling tunnel, a hole in space, maybe a portal. But a black hole isn't a hole at all, not like the ones you dig in soil or find in your socks. It's not empty. It's not even dark in the way night is dark. It is gravity, pure, undiluted, intense, so strong that even light, the fastest thing in the known universe, cannot outrun it. To understand where black holes come from, we begin with stars, not the tiny dots you see above your head, but the massive, ancient giants that live for billions of years. Stars are born in clouds of gas, mostly hydrogen, drifting in cold regions of space. When enough gas gathers in one place, gravity begins its quiet work, pulling it inward, tighter, hotter. At a certain point, the pressure becomes so great that hydrogen atoms begin to fuse into helium. This is what powers a star, nuclear fusion, an inward pull of gravity balanced by the outward push of energy. It's a perfect dance of pressure and light, and for most of a star's life, that balance holds. But eventually, the fuel runs low, fusion slows, and gravity, always patient, always waiting, begins to win. In smaller stars, this collapse ends gently. A white dwarf might form, hot, dense, but stable. In larger ones, the end is more dramatic, a supernova. The outer layers explode outward in brilliant light, while the core collapses inward with unimaginable force. Now, if the star was very massive, say over 20 times the mass of our Sun, the collapse doesn't stop. There's no pressure strong enough to resist. The core keeps falling inward, beyond atoms, beyond protons, beyond anything we can truly imagine, and it forms a black hole. But here's the strange part. The black hole itself has no surface, no solid crust, no glowing shell. There is just a boundary called the event horizon, the point of no return. Once something crosses that line, it cannot escape. Not light, not time, not you, not even a whisper can get out. Inside, everything falls toward the center, toward what we call a singularity, a place of infinite density, where all our equations break and the known rules of physics quietly dissolve. It sounds scary, doesn't it? But a black hole is not violent. By nature, it doesn't suck things in like a vacuum. It doesn't roam the galaxies swallowing stars. If the Sun were replaced by a black hole of the same mass, Earth would keep orbiting it just as calmly as it does now, just darker and much colder. You could even fly near a black hole, and as long as you stayed outside its event horizon, you'd feel a pull, sure, but no instant doom. From afar, black holes are quiet, still patient. They don't chase, they wait. Now, here's something else to wonder about. Time behaves differently near a black hole. Imagine you're floating in space near one, and your friend stays far away. Hold up a clock. From your perspective, it ticks normally. But from your friend's point of view, your clock ticks slowly. Your voice seems to stretch out. Your movements look like they're happening underwater. This effect is called gravitational time dilation. And it's not science fiction, it's pure. Time truly passes more slowly near massive objects. Right now, even here on Earth, your feet experience time just a tiny bit slower than your head because they're slightly closer to Earth's gravity. It's a small difference, but it's real. And near a black hole, the effect is extreme. So, if you were to hover just above a black hole's event horizon, and you could look back at your friend, you might watch thousands, even millions of years pass in their world while only a few minutes pass in yours. That's the strange magic of black holes. They don't just bend space, they bend time. They fold the fabric of reality itself. You may be wondering, if light can't escape, how do we even know? Black holes exist. We don't see the holes, we see their footprints. We see stars orbiting nothing, being whipped around by an invisible presence. We see gas swirling in, heating up, glowing fiercely before it crosses the event horizon. We see X-rays, light distance, and sometimes even a shadow, like the one photographed by the Event Horizon Telescope in 2019, the first image of a black hole's boundary. We see how black holes shape galaxies, how they anchor vast arms of stars, how they quietly sculpt the universe. They're not monsters, they're more like librarians, quiet keepers of endings. But even these endings have beauty, because black holes are part of the life cycle of the universe. Then that black hole waits and watches, and perhaps someday it finds another. And when two black holes meet, something extraordinary happens. They don't collide like rocks. They spiral together in a slow, inevitable embrace. Their gravity intertwines, their horizons stretch toward each other, and they merge, not exclusively, but powerfully, invisibly, released not as light, but as ripples in the fabric of space itself, gravitational waves. In the next chapter, we'll float gently into that strange idea. What is gravity really? What does it mean to feel a pull even when nothing touches you? What quiet force is holding your body to the bed right now and calling black holes into one another's arms? Close your eyes, breathe in, breathe out. It's not loud. It doesn't buzz like electricity. It doesn't knock or shout. It's a constant, invisible hand and pressing you gently into your bed, cradling your weight, holding you close to earth, as if to say, stay, and so you do. You don't think about it much. You don't have to, but gravity is there beneath your skin. It moves through you every second of your life. It tells the oceans where to swell, the moon where to hover, and the stars where to burn. It is quiet, but it is not weak. In fact, gravity is the reason there are stars. It is the reason anything exists at all. Let's float into that for a while, softly, slowly, as the night deepens. Imagine the universe, long ago, before galaxies, before planets, before light, just clouds, cold and scattered, and still, then, in that silence, a slight gathering, a drifting of matter into clumps. Gravity begins to work quietly at first. It doesn't rush. It doesn't need to. It has infinite patience. Over time, longer than mountains. No, longer than oceans, remember? These clumps grow dense. They pull more matter toward them. They tighten, heat rises, pressure builds. And then, suddenly, a star fusion begins. Light bursts into the universe. But what is gravity really? It's tempting to say it's just a pull, an attraction between two things with mass, but that's not quite true. That's only the surface. Let's use a metaphor. Close your eyes and picture space, not as emptiness, but as a soft, invisible fabric, a vast, endless quilt stretched out in every direction. Now place something on that fabric and say, a ball, a planet, a step. The fabric curves beneath it just a little. If you roll a smaller ball nearby, it moves towards the bigger one. Not because the large ball reached out and pulled, but because the fabric beneath it curved. This is the heart of Einstein's insight. Gravity is not a force pulling across space. Gravity is the shape of space. Mass tells space how to curve, and curved space tells objects how to move. That's why the moon doesn't fall into Earth, is moving in a curved path through space, held not by a rope, but by the shape of the world's presence. And that's why black holes are so strange. They aren't things sitting on the fabric. They are punctures in it. Deep, steep curves from which even light cannot climb out. Their gravity isn't just strong, it's extreme geometry. You right now are held in that geometry. Earth presses into spacetime, and spacetime curves softly around you. That's why you feel weight. Not because something is pushing down, but because space is guiding you toward the planet's center, and your body gently resists. When you drop something, a pen, a pillow, a thought, you're watching it fall along the lines that space has drawn. You can't see those lines, but they are there, drawn by Earth's mass, followed by every falling leaf and every orbiting moon. And though it feels ordinary, it's anything but. Think about this. Every time you jump, even slightly, you are temporarily resisting the pull of an entire planet. You leave the surface, you fight gravity for a breath of a second, and then you return, always gently back to Earth. Even in space, astronauts are still held by Earth's gravity. They're falling, too, just sideways, fast enough to keep missing the ground. That's what an orbit is, falling forever without hitting anything. The same is true for the moon and satellites and stars in galaxies. They all move through space like fish in invisible currents, guided not by strings or engines, but by the quiet shape of gravity. And black holes, they are the deepest currents of all. Their gravity isn't a simple slope, it's a steep drop, a waterfall in the fabric. Once you cross the edge, the event horizon, there is no way back upstream. Not because something is chasing you, but because the river of space has turned downward, and time itself flows differently inside. Sometimes two black holes find each other across vast distances. They drift closer, drawn not by hunger or desire, but by the elegant inevitability of curved space. Their gravity overlaps, their motions change, and a slow spiral begins. No splash, no bang, just a steady circling for thousands, millions, sometimes billions of years, like two dancers who don't even know they're dancing yet. As they move, their paths create ripples, tiny waves in the fabric of space. Gravitational waves, they are soft, gentle pulses, stretching space here, squeezing it there. These waves travel outward across galaxies, carrying the story of the spiral. Some will travel for 100 million years and then pass unnoticed through the soft skin of your body. You don't feel them, but they are real. They are the whispers of black holes in motion, messages written in gravity itself. And so tonight, as you breathe, you are part of that story. Gravity holds your breath. It holds your heart. It holds galaxies and slow spiraling arms. It is both comfort and mystery, the most familiar force and the least understood. So the next time you drop something or feel the weight of your body settle into sleep, remember you are moving through curved space, and gravity, quiet as breath, is drawing you gently home. But if gravity can ripple, can whisper across space, then what are these waves really? How do we hear them? How do we know two black holes have become one? Let's drift deeper into that next. There's a hush in space so deep it feels eternal. But silence doesn't mean stillness. Even in the quiet, things move, things turn, things draw together. And somewhere, not in a place you could point to, but in the grand deep of the cosmos, two black holes begin to spiral. They are invisible to your eyes, not because they're hiding, but because they don't reflect light. They are weight, not color, a we, not glow. But if you could see the fabric of space itself, if your well mind could paint the universe in contours and curves, you'd watch them circling slowly at first, then faster, not like dancers on a ballroom floor, more like whirlpools in the sea, pulling, tightening, growing closer. This is no chase. It's not chaos. It's a rhythm, deep, patient, mathematical. Every orbit brings them nearer, and as they spin, they speak. Not in sound no one can hear in the vacuum of space, but the black holes speak in waves. Not waves of water or light, but gravitational waves. Imagine a calm lake, still and perfect. Now drop a stone into it. The ripples spread gently, rhythmically outward, in all directions. That's what black holes do when they orbit one another. Their motion disturbs the very shape of space. They send out ripples, invisible and vast gravitational waves, a language written into spacetime itself. These waves don't move through space. They are space stretching and compressing as they travel. Every time the black holes circle, another wave forms, and each wave carries a message. We are here. We are moving. The waves that pass through you are unimaginably faint, smaller than the width of a proton, but they're real. They bend you just slightly, then they move on. The black holes have danced, and you have felt the echo, even if you didn't notice. As their orbit tightens, the black holes spiral faster. The energy of their motion pours into the fabric of space, and the waves grow louder. In gravity's voice, to us, this louder is a frequency, a chirp, a rising tone like the coiling of a spring. When scientists record it, it almost sounds like a bird calling the void. But that sound isn't traveling through air. It's not sound at all, it's movement. The movement of space, the whisper of a universe rearranging itself. It wasn't until 2015 that humanity heard this dance for the first time. The instruments were enormous, arms stretching for kilometers, lasers bouncing between mirrors, measuring the tiniest trembling in space. LIGO, the laser interferometer, gravitational wave observatory. It listened for nothing, and then it heard something. A ripple, a wave, a whisper that had traveled for 1.3 billion years. Two black holes had merged in a distant part of the universe, and Earth, all that time later, wobbled just slightly as their wave washed through us. It was the first time we didn't just see the cosmos. It's real, measured, witnessed in the trembling of instruments and the shiver of space. Two black holes, once alone, find one another. Drawn by gravity's logic, by mass and distance and time, their spiral accelerates faster, tighter, their orbits blur. And then the moment, the merger, their horizons touch, their centers unite. A single larger black hole is born. And the final wave, the last ripple, rings out across the universe. A goodbye, a birth cry, a memory. But even after the merger, the new black hole quivers. It's not quite still yet. It vibrates, a cosmic bell struck once, echoing quietly into silence. This too sends out waves, fainter now, the closing chords of a symphony that lasted billions of years. So here you are, breathing quietly on a small planet, listening to a dance that once unfolded when Earth's first animals were just beginning to dream. A dance you cannot see, a sound you cannot hear, but a story that touched you nonetheless. Isn't that remarkable, that the most massive, mysterious things in the universe, black holes born from stars, can move in such harmony, can circle in silence, can merge in grace, and that their echo, soft and strange, can pass right through your bones? Tonight, the black holes rest. Their story has been told in waves, but the waves themselves, these ripples in space, still travel. They stretch onward, far beyond Earth, beyond our galaxy, heading deeper into the dark. What are they made of? What carries them forward so gently and so far? To answer that, you must understand space itself, not as emptiness, but as something, a fabric, a shape, a quiet field that bends and sways. Let's float into that next, into the cloth that holds the universe. Time feels so steady here, doesn't it? Ticking seconds, soft breaths, the rise and fall of your chest. the quiet rhythm of night falling across your body like a blanket. But time is not what it seems. It's not the same everywhere. And the deeper you drift into gravity's arms, the stranger time becomes. So tonight, we lie at the edge of something ancient, a black hole, and we watch how time changes. Not with a jolt, but with a slow, dreamlike distortion. Imagine floating in space near a black hole. You're safe. You're not falling in. You're hovering just outside the event horizon. That invisible boundary where space folds inward and time begins to shift. You hold a clock in your hand. It ticks softly, 1 second, then another. You feel normal. Nothing has changed. But imagine your friend far away, floating in open space where gravity is weaker. They're watching you through a telescope, and they see your clock too. And from their view, something strange is happening. Your seconds are stretching. Your movements are slowing. It's called gravitational time dilation. A soft but powerful truth discovered in Einstein's theory of general relativity. The stronger the gravity, the slower time moves. Not metaphorically, literally. Time, the thing you think of as constant, becomes elastic, closer to Earth's surface. Time passes just a tiny bit slower than it does in the clouds above. GPS satellites orbiting our planet have to adjust their clocks because time ticks faster for them up there than it does down here, and near a black hole, that difference becomes enormous. Hover just above a black hole's event horizon, and time for you could crawl while the rest of the universe races ahead. If you stayed there just floating for a few minutes, your friend might experience years, centuries, eons. You could return, and the world you knew would be gone. All while you felt only a single breath pass between heartbeats. This isn't fiction. It's not a thought experiment. It's reality, confirmed, tested, deeply woven into how gravity works. And black holes are its most extreme expression. So what happens if you cross the edge? You drift beyond the event horizon, slowly, peacefully. There's no crash, no sudden shift, no line you can see or feel. From your perspective, you fall inward normally. Your body stretches, and not physically, but in time. You become an echo lingering forever at the threshold. Eventually, even your light can't escape, and you fade from view. Strange, isn't it, that something as familiar as time can bend, stretch, break? But in a way, that's what makes time so gentle. It adapts, it listens to gravity, it slows down when it's needed. And as you lie still, your own time flows in its delicate rhythm. Maybe it's comforting to think that time isn't racing, that it can breathe with you, that in the presence of great mass, time grows patient. Now imagine the moment just before two black holes merge. If you could watch the last second before they touch, you'd see it stretch into a long pause, a slow exhale. But for the black holes themselves, there's no pause at all. They touch, they merge, they become one. The event horizon reshapes, a new boundary is born. Time resumes its quiet flow, and in the space around them, the final ripple of their union escapes. A gravitational wave sent outward like the softest farewell. You lying still now have always lived in time's river. It carries you from moment to moment, from childhood to now, from now to tomorrow. But black holes remind us that river isn't the same everywhere. It can trickle or rush, it can pause, it can twist, and perhaps that's what makes time precious. Not that it's always fast. It can stretch to hold memories. It can slow at the edge of mystery. So what would it feel like to rest just above a black hole? To float where time is syrupy and thick, where a heartbeat lasts a century, where gravity bends not only your path but the seconds between your thoughts. Would you feel the stillness more deeply? Would you sleep more slowly? Would dreams last longer? Or would time itself feel like a dream? Tonight, time stretches just a little for you. Not because you are near a black hole, but because you're allowing your mind to wander gently, to drift, to slow down. And even though the earth spins and clocks tick, you're allowed to pause, to float, to stretch your seconds like silk. Because sometimes the most powerful thing you can do is to slow down, to rest in the gravity of the present moment. But if time can slow, can it ripple? Can we feel those ripples? Let's learn how we heard the whisper of space trembling with memory. Somewhere in the night sky, a star is dying. It does not cry out. It does not flicker with fear. It simply reaches the end of its long, burning life. To understand where black holes come from, you must begin here. Not in darkness, but in light. Because every black hole begins with a star. Picture one now, massive, luminous, ancient. Its body is made of hydrogen. Its surface churns with heat flares, magnetic storms, but inside, a delicate balance holds. Gravity pulls inward, fusion pushes outward, and the two remain locked, not in battle, but in quiet agreement. This balance is everything, but no fuel lasts forever. At some point, after millions, maybe billions of years, the star begins to change. It runs low on hydrogen, then fuses helium, then carbon, then heavier and heavier elements until it reaches iron, and iron, unlike the others, does not release energy when it fuses. It only takes. The star can no longer hold itself up. The balance breaks. In that moment, so brief, so final, gravity wins. The star collapses, not gently, not slowly. Its core caves in. Atoms are crushed. Protons and electrons are squeezed into neutrons. Light is trapped. Matter folds in on itself. The outer layers explode outward. A supernova brighter than an entire galaxy for a few heartbeats. A last defiant blaze, and then silence. What remains depends on the star's size. If the star is small, it might leave behind a white dwarf, hot and dense, but peaceful. If it's heavier, a neutron star, a city-sized ball of matter, so dense that a spoonful would weigh more than a mountain. But if the star is massive enough, far beyond our sun, even neutrons can't hold back the collapse, and the core continues to fall inward, beyond resistance, beyond light, and there a black hole is born. It doesn't explode into existence. It doesn't announce itself. It simply becomes a place where the escape velocity, the speed needed to leave, is faster than light. A region where nothing returns. Not light, not time, not sound. A boundary forms the event horizon. Inside, matter spirals toward a central point, a singularity, a place so dense, so strange that physics itself no longer knows what to say. But all of this happens from a beginning of brilliance, a star, a fiery nuclear engine, a life lived in light. It is not a story of destruction. It is a story of transformation, of something so full of energy that it could not contain itself forever. You may wonder, how often does this happen? More than you might think. In our galaxy alone, there may be millions of black holes, quiet, hidden, drifting. They don't shine. They don't call attention to themselves, but they are there, waiting in the spaces between stars, moving through the fabric of space. Some are born from a single collapsing star. Others, much larger, may form from many mergers, from galaxies colliding, from histories stacked upon one another. These are the supermassive black holes, millions or even billions of times more massive than our sun. And nearly every galaxy has one at its heart, even ours, yes, says, at the center of the Milky Way. 26,000 light-years from where you lie now, there is a black hole. Spins slowly, pulling stars into orbit around it. Invisible to the eye, but longer than Earth has had oceans, longer than mountains have stood. A reminder that black holes are not just ends, they are anchors. Even now, above your head, massive stars are burning. Some will live quiet lives, cool and dim and slow. But others, the giants, will end as black holes. They will vanish, not with a scream, but with a fold. Their mass remains, their gravity deepens, their light disappears, and a new silence enters the cosmos. This silence is not empty, and perhaps someday another black hole will drift nearby, and the two will circle, spiral, merge, and send out a message not of the star that died, but of the union that followed. So, you see, black holes are not monsters. They are memories, stories told in gravity. They are born from light, shaped by collapse, and carried forward in silence. You followed one star to its end. But even in that end, the universe is not finished speaking, because from that end comes a ripple, a signal, a soft stirring in the cosmic fabric. And the question becomes, how do we feel that wave? How do we know from so far away when two black holes become one? Close your eyes, breathe slowly, and let's begin to listen. And yet the universe still speaks. It speaks through gravity, through motion, through shape and rhythm. And when two black holes find each other and begin their slow spiral inward, their conversation begins not with light, not with sound, but with ripples. Imagine spacetime, the fabric of everything, as a soft, invisible ocean. Most days it is still peaceful, smooth. But when something massive moves, a star collapsing, a black hole spinning, or two merging, it sends out ripples. These are gravitational waves. When a gravitational wave passes through you, it gently, very gently, stretches you taller and thinner, then shorter and wider, then returns you to normal. You won't feel it, you won't notice, but your atoms do. The space between them changes briefly, minutely, beautifully. Gravitational waves are the language of black holes, their footprints, their whispers, their sighs, and in their motion, they shake the universe. Like a bow drawn across a violin string, they make space hum. When two black holes orbit each other, they do so silently. But each rotation sends out a wave. As the orbit tightens, the waves grow stronger, faster, closer together. It's a rising pitch, a cosmic crescendo, until the moment they merge, and the final wave rings out. It's not a boom, it's not a flash, it's more like a bell struck once, and that note, that ripple travels on across galaxies. How could we possibly feel a tremble in space, so small it's less than the width of a proton? Because we've built instruments that can hear space breathe. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. Two long arms stretching, 4 kilometers each, shaped like a giant L inside each arm. A laser bounces between mirrors. When a gravitational wave passes through, it stretches one arm ever so slightly and compresses the other. It sings a new interference pattern, a tiny flicker, a whisper caught in light. And that whisper is recorded, analyzed, transformed into a sound wave we can hear, and it goes chirp, just like that. A tiny chirp, a signature of 2 black holes merging, perhaps a billion light-years away. A memory arriving late, but perfectly intact. The first time LIGO heard that chirp, on September 14th, 2015, we confirmed something that had only been theory before, that black holes merge, that they ripple space, that those ripples reach us. We were listening, and the universe answered. Dozens of events, each one a new pair of black holes colliding, each with its own mass, its own rhythm, its own voice in gravity's language. Some were light, small black holes dancing quickly. Others were massive, slow, heavy spirals that ended in thunderous waves. Some even came from neutron stars, merging, dense remnants of stars that still had light to give. Those events gave us both gravitational waves and a burst of light, a beautiful duet. But the black holes, they remain silent in light. Their stories are told only in motion. You feel it indirectly through trembling space, through the waves that space-time carries gently across the void. And the best part, these waves are still traveling. A merger that happened a billion years ago might only now be arriving at Earth. It passes through us, through our planet, through our bodies, and then continues on to stars we've never seen, to galaxies beyond our reach. Gravity remembers, and it carries that memory endlessly forward. You might wonder, if space can ripple, can it also tear? Can gravitational waves grow so strong they break the fabric of reality? The answer is not in the way we think. Even the strongest gravitational waves we've detected are gentle. The universe is vast and its fabric is flexible. Waves pass through it, but they do not destroy it. They move like breath, like pulse, like time itself. And so tonight, as you rest, space is still stretching quietly, softly, all around you. Not a song, a story without light, and you are part of that story now. You've learned to listen to a language that doesn't need sound, to waves that carry memory, not meaning. And those waves, if we follow them backward, lead us to something even more profound. What exactly is this space that ripples? What fabric stretches and carries these waves so far? But what is space-time made of? Let's float into that next. Into the cloth of the cosmos. The universe is full of motion. Planets orbit, stars flare, galaxies spin. They do not rustle leaves. They do not echo through air. But still, somehow, we've learned to listen. On a quiet stretch of land in Hanford, Washington, and again in Livingston, Louisiana, 2 enormous ears stretch across the earth, each one 4 kilometers long, each one made not of flesh and bone, but of laser, light, and silence. These are the twin observatories of LIGO. The Laser Interferometer, Gravitational Wave Observatory, 2 places built to hear the universe breathe. And across the Atlantic, in Italy, another detector, Virgo, listens to together. They form a growing chorus of instruments, tuned not to light or heat, but to space's subtle trembling. Imagine this. You take a flashlight and point it down a long hallway. You split that. At the ends, mirrors reflect the beams back to their starting point. When the beams reunite, they form a pattern, a signature of how far they've traveled. Now imagine that a gravitational wave passes through the hallway. It doesn't knock over the flashlight. It doesn't shake the building, but it stretches one path slightly and compresses the other. The beams returning are no longer perfectly in step. Their pattern changes. And from that tiny flicker of interference, we know something has stirred the fabric of space. That's what LIGO does. At its heart, it's a device for measuring distance with astonishing precision. How precise? LIGO can detect a change less than 1,000th the width of a proton. A shift so small, it's like measuring the distance to the nearest star to within the width of a human hair. This sensitivity is not an accident. It's the result of decades of planning, of collaboration, of engineering that borders on poetry. LIGO and Virgo are built in pairs, not just for redundancy, but for certainty. If both detectors feel the same wave at nearly the same time from slightly different angles, we can triangulate where in the sky it came from. We can say that a ripple passed through, a story arrived. These instruments are not listening once. They are listening always, day and night. Through storms and stillness, they wait. They listen for the tiniest pause in the universe's breath, and when it comes, they ring. Not loudly, not in panic, but in recognition. On September 14th, 2015, they rang together. For the first time in history, humanity heard the sound of two black holes merging. It lasted less than half a second, a faint rising chirp, but that chirp came from 1.3 billion light-years away. Two black holes spiraling inward, crashing together, becoming one. And their final sigh, their last ripple, reached us. And we listened. That moment opened a new chapter for science. For thousands of years, we have studied the sky with our eyes. Telescopes made it clearer. Cameras captured its beauty. But light can be blocked, absorbed, hidden. Gravitational waves, on the other hand, pass through everything. They travel through dust, through stars, through time, through you. They do not stop, they do not fade, and now we can hear them. With every wave we catch, we learn something new. We've heard heavy black holes merging, more massive than we expected. We've heard neutron stars colliding, spraying out gold and platinum into space. We've begun to map the cosmos, not by its light, but by its motion. It's as if we were deaf, until now, watching a silent film of the universe. And suddenly, sound, a sound without air, a sound made of space itself. And now that we've heard it, we'll never go back. New observatories are coming. Kagra in Japan, LIGO, India, and far in the future, LHSA, a space-based detector that will orbit the sun, listening with arms 2.5 million kilometers long. Together, they will form a global network, a celestial stethoscope against the chest of the universe, listening, always listening. And perhaps years from now, a wave will pass through your city, through your home, through your sleeping body. It will come from some distant collision from black holes that lived and died before Earth had trees, before oceans had fish, and you will not feel it. But LIGO might, Virgo might. The world might tremble just for a moment, and another story will unfold. You don't need to be a scientist to appreciate this quiet magic, to feel awe that we've built machines so still, so patient they can hear the whisper of spacetime itself. Tonight, as you lie here, your breath slow and steady, you are sharing this world with instruments that do not sleep. They are listening to the void, not for silence, but for movement, for memory, for truth. And the waves they hear, they don't just tell us what happened. They remind us that space is not empty. It has shape, it has depth, it has texture, it can be moved. But what exactly is it made of? What is this fabric that trembles and flows? Let's drift there next, into the soft, curved cloth that holds every star in place. Close your eyes for a moment and imagine space not as emptiness, but as something soft, a fabric, a stretch of silk drawn across the cosmos, smooth, curved, dimly shimmering. This is spacetime. It sounds abstract, even mysterious, but the idea is beautifully simple. Space and time are not separate. They are one single thing, a connected field, and everything in the universe moves through this field. Imagine you're holding that silk in your hands, flat, still, untouched. Now place a marble on it. The fabric bends. A small dip forms around the marble. That dip is gravity. Now, roll a smaller marble nearby. It curves inward, not because the marble pulled it in, but because the shape of the fabric guided its path. This is how gravity works, not as a force pulling at a distance, but as a curve in the soft geometry of spacetime. It was Albert Einstein who gave us this image, that mass and energy shape the space around them, and that space tells objects how to move. It's a quiet conversation. Here's the shape, says the planet. Then here's the path, replies the moon. And so the moon doesn't orbit Earth because it's being yanked by an invisible rope. It moves along a valley in curved spacetime like a marble swirling around a bowl, guided by the very landscape beneath it. This fabric, this spacetime, stretches everywhere. It holds your body to the Earth. It keeps Earth tethered to the sun. It lets galaxies spin in spirals, and it stretches between stars like threads you can't touch. Right now, this moment, spacetime is beneath you, around you, in you. Your very breath flows through this invisible field, and every step you've ever taken has bent it just slightly. Even you, your body, your mass press into spacetime, leaving the smallest, softest dent. Now think again of that stretched sheet. What happens if you place something very massive on it? A planet makes a small valley. A star creates a deep well. But a black hole doesn't just make a dip. It makes a tunnel. A pit so steep that nothing, not even light, can climb out. Not because light is too weak, but because the very shape of space has turned downward. There is no path out, only in. This is why black holes are invisible. Not because they are hidden, but because the path light would take to escape no longer exists. But even black holes do not tear the fabric. They bend it, they stretch it, they deepen it, and when they move, orbiting one another, for instance, they send out waves in this cloth, gravitational waves. You felt them already in stories, in the chirps heard by LIGO, in the ripples sent from merging black holes. There are not sounds in air, but movements in the very structure of existence. The fabric flexes, it recovers, and the wave continues. On space-time is elastic, not in the way rubber is elastic, but in the way water is able to flow, to ripple, to carry motion across great distances. It's soft to motion, but firm to into structure. It can hold galaxies in place for billions of years, and still ripple with a whisper from two colliding black holes. It is the most delicate strength you can imagine. This idea of a fabric of reality may feel like metaphor, but scientists treat it as real. It predicts things. It explains how light bends around stars. It tells us how time slows near massive objects. Even GPS satellites must account for the curvature of spacetime and around Earth to stay accurate. Without those tiny corrections, your phone would get lost within minutes. So when you walk outside and look up at the stars, you're not just looking into distance. You're looking across structure, a quiet, invisible architecture that holds everything in place. That star shining faintly in the night, its light has traveled along the curves of spacetime, bent slightly by gravity, carried steadily toward your eyes. Its path is not straight, but graceful, shaped by every mass it passed on the way. And your path, too, has been shaped by this cloth. Every fall you've taken, every leap, every orbit, every drift into sleep, guided by the gentle curves beneath your feet. You are moving through spacetime right now, even as you lie still, even in sleep, because time itself is part of the fabric, and you're always moving forward through it. It's comforting, in a way, to know that space is not emptiness, that time is not just a ticking clock, but that together they form something soft, something shaped, something that holds you. You're not floating in nothing. You're resting in a web of gentle structure woven from gravity and geometry, and black holes, those strange, quiet wells, are simply deep dimples in that web, places where space-time curls in on itself, folds inwards, and keeps its secrets. So, next time you close your eyes and feel stillness, remember, stillness is relative. You're moving through time, through space, through the slow, curved fabric that wraps the stars, that stretches like silk, that remembers every mass, every moment, every ripple. And if this fabric holds the stars and carries waves of gravity, can it also hold something else? Information, memories, particles, the stories of what falls into a black hole. Because if a black hole eats everything, where does everything go? Do the things it swallows disappear forever? Or does the universe find a way to remember? Let's wonder about that next. Somewhere in the quiet dark, far from any star or moon, two black holes are circling each other. Not quickly, not yet. For now, their dance is slow, ancient, a rhythm that has taken millions, maybe billions of years to reach its end. Each black hole bends the spacetime around it. Two deep wells moving through soft fabric, stirring invisible currents. And as they circle, they draw closer, spiral tighter, move faster, not because they are rushing, but because the space between them is shrinking. The fabric itself is pulling them in. This is the final act. Two giants in motion, the heaviest objects in the universe, locked in an embrace. They don't collide like rocks. They don't crash. Instead, they fall inward again and again, closer and closer, until they are only moments apart. Their mass curves spacetime so deeply that even time stretches thin. The world around them seems to speed up, but inside their orbit, time slows down. The spiral tightens, the waves grow louder, not in sound, but in gravity. You've heard these waves before, felt them in earlier chapters. These are the gravitational waves, the ripples sent out when two massive objects move in curved space. And now, as the black holes near one another, the waves rise in pitch faster, stronger, until the final note is ready to sound. And then, in a moment that lasts less than a blink, the horizons touch, not gently, not violently, just completely. Their boundaries become one. The singularities inside those points of infinite density fall together. And what remains is not two black holes, but one larger, heavier, calmer, and the universe in response shivers. The final gravitational wave spreads outward, a sharp, rising chirp, a single exhale, a last ripple before the new black hole settles into itself. That ripple travels for millions of years. It passes through galaxies, nebula, stars, and someday it passes through Earth, through the soil, through the buildings, through you, not with force, but with grace, a flicker in spacetime, a moment where everything stretches and compresses just a little, and then continues on. This is how we know the giants have collided. Not by looking, not by hearing, but by feeling, by watching space itself move. The chirp LIGO hears, the signature Virgo confirms, is the final echo of two black holes merging. It lasts just a fraction of a second, but that sound tells us everything. How massive they were, how far away, how long they danced before joining. You might ask, what happens to their mass? Does anything disappear in the merger? The answer is yes, but not in the way you think. Some of the combined mass doesn't go into the final black hole. Instead, it becomes pure energy released in gravitational waves. In some cases, the energy released is more than the light of all the stars in the visible universe combined. But we don't see that light. We don't feel that heat. We feel the movement, the ripple, the story. After the merger, the new black hole quivers for a moment. It's not perfectly round yet. It rings a dying tone, a cosmic bell settling after a strike. This ringing also sends out waves, fainter, but just as real. And then finally, stillness. The new black hole is quiet, silent, complete. Nothing escapes it. No light, no memory, only mass, only gravity, only the story written into the waves that left before the horizon closed. In this silence, there is no mourning. The universe does not grieve the two black holes because something new exists. A heavier black hole, a deeper well, a new mark on spacetime. It may stay alone forever, or it may one day meet another, and the spiral may begin again. The cycle is not destructive. It is creative. The cosmos remakes itself through collision, through gravity, through waves. You lying still now are not far from this story, because these events, these cosmic fusions, are not rare. They happen all the time. Every few minutes perhaps, somewhere in the vastness, unseen, unheard, but not unfelt. Each one sends out a message, a gravitational ripple, a change in the curvature of space. And sometimes those messages reach us, reach you. When giants collide, they do not make noise. They make motion, they make memory, they make something new. Their dance ends, but the ripple continues. And in that ripple is encoded a record of time, of mass, of shape, of loss and gain. The language of gravity is precise, but it is also poetic. It does not use words, but it tells stories all the same. And so you might wonder now, if black holes merge and form something new and send out these graceful waves, where do those waves go? How far can they travel? Do they ever fade? Or do they echo forever in the soft cloth of the cosmos? Let's follow one of those waves into the distance. Let's trace the echo as it moves through galaxies and stars and us. Let's drift into the afterglow, into the energy that lingers when the giants are gone. Black holes do not burn, they do not shine, they do not radiate light in the way stars do. And yet, when they merge, when two of them become one, they release more energy in a moment than 1,000 stars would in their entire lives. It's just not the kind of energy we usually see. It's not warmth, not flame, not color. It's gravity moving. It's space itself stretched, flexed, ringing like a bell that cannot be heard and only felt. Let's return for a moment to that final spiral, to black holes circling one another, closer, tighter, faster. Their combined mass warps the space around them into steep, rolling curves, and as they orbit, they lose energy, but they don't shed it in light. They shed it as gravitational waves, ripples in spacetime that carry energy outward at the speed of light. This is how the orbit shrinks. This is why the spiral tightens. Each wave takes a little more energy with it, and the dance grows faster. You might imagine gravitational waves as tiny messengers delivering packets of motion to the universe. And when the black holes finally merge, those packets become an avalanche. In a fraction of a second, more energy is released in gravitational waves than all the light from all the stars in the observable universe combined. But you wouldn't see it. You wouldn't feel heat if you were nearby, say a safe distance from the merger. The most you'd experience is the space around you gently stretching, then compressing, then returning to stillness. The power would pass through you without a sound. Let's speak in numbers just for a moment. Imagine two black holes merging, each one about 30 times the mass of our sun. After the merger, the final black hole might weigh 58 solar masses. What happened to the other two? Those two missing suns didn't vanish. They were converted and entirely and into gravitational wave energy. E equals mc to energy equals mass time the speed of light squared. And the speed of light squared is a very, very large number. Even a little mass becomes an ocean of energy. And this is not a little mass. This is entire stars becoming motion in the fabric of reality. But that energy doesn't stay in one place. It travels. It becomes a wave expanding outward in every direction through galaxies, through nebula winds. And after 1 billion years, it might reach Earth. We don't see it. We don't glow. But the planet moves just slightly. Not shaken, not stirred, just stretched for the briefest moment. A single ripple, a say. The amazing part is not just how much energy is released, but how gently it arrives. Gravitational waves do not batter or burn. They do not blast or blind. They pass through you as if you are light yourself, transparent, threaded into the fabric they move through. And yet, with the right instruments, patient machines like LIGO and Virgo, we can capture them, measure them, listen to the echo of stars that became shadows and shadows that became waves. You might be wondering, where does that energy go? Does it keep traveling forever? The answer mostly is yes. Gravitational waves fade slowly, very slowly. They grow fainter as they spread like ripples on a still pond, but the pond is infinite. Some part of that energy is still out there moving, traveling. Maybe one ripple is passing through a distant galaxy now, brushing against stars that don't even know they're being touched. Maybe another has already passed through your body so gently you never noticed, but it changed space just a little, and you were part of that moment. This is the quiet beauty of gravitational energy. It is not showy, it is not loud, it is persistent. It moves without needing to be seen. It connects distant events across unimaginable distances. It tells us that what happened there can still be felt here, even if we arrived late to the story. Black holes in this way are not just endings, they are instruments. Each merger plays a note in the symphony of spacetime, and gravitational waves carry that music forward without ever needing a stage. They tell us what happened, when, and how massive the players were, and all we have to do is listen. So tonight, as you lie still, think about how much energy it takes to light up the sky with stars. Now imagine that same power compressed into silence. No flame, no brightness, just motion. And yet somehow more powerful, more enduring, carried on waves that cannot be stopped, only followed. And maybe the most astonishing part is this. We didn't even know we could listen until recently. We built instruments with the patience of trees and the precision of moonlight. And they told us, yes, the waves are real. Yes, the giants merged. Yes, the universe remembers. But energy is only part of the story. The waves carry motion, but also possibly memory. And that leads us to an even stranger question. When something falls into a black hole, matter, light, information, does it disappear? Does the universe forget? Or is there a secret way the black hole holds what it swallows? Let's float into that mystery next, where physics begins to whisper about information, entropy, and the memory of light. There is a stillness after every great event. After lightning flashes and thunder rolls, the world holds its breath. The air seems thicker, time slows, the storm passes, and in its place, silence. The same thing happens in space. Even there, in the soundless, frictionless void, a kind of calm follows every collision. After black holes merge, after their last ripple escapes, there is quiet again. Deep, enormous, perfect quiet. The new black hole just formed is not entirely at rest. Not yet. It vibrates. It wobbles, ever so slightly, like a struck bell, like the surface of a pond that has just swallowed a stone. These final vibrations are subtle but powerful. They send out a few last gravitational waves, faint soft ripples from the newborn black hole as it settles into its new shape. Scientists call this moment the ringdown, the phase after the merger, when the remnant black hole adjusts, resonates, and then finally relaxes. It's hard to picture something as heavy and dark as a black hole ringing. But in the language of physics, that's what it does. Not with sound, but with motion. The shape of the event horizon, the invisible boundary beyond which nothing escapes, quivers for a fraction of a second. It isn't perfectly smooth. It flickers, wrinkles, then returns to stillness. If you could stand safely near it, not too close, but not too far, you wouldn't see these vibrations. You wouldn't hear them, but you would feel them in the changing geometry of spacetime. You would feel space stretch and settle. You would sense time easing back into its normal rhythm. And then, as if nothing had ever happened, all would be still. The black hole becomes quiet, not because it forgets, but because it has no more to give. No more motion, no more waves, just presence. Immense, silent, final. It has swallowed its partners. It has reshaped itself, and now it waits. What does it wait for? Maybe another partner, drifting slowly toward it over 1 billion years. Maybe nothing. Maybe this black hole will remain alone for the rest of the universe's life. And that's okay, because the story doesn't end here. Not really. The ripples from its merger still travel. Even if the black hole forgets, the universe remembers. Gravitational waves stretch outward in all directions, carrying with them the full memory of the event, the masses, the motion, the timing, the energy. These waves are history, a record written into the fabric of space. No ink, no paper, just curvature, just form, just truth. And we are learning how to read that record. Each ripple that reaches Earth adds a new page to our growing book of the cosmos. We map what we cannot see. We listen to what cannot be heard. And in doing so, we extend our reach into the most distant past. But here's something strange to consider. After all this motion, the final black hole looks ordinary. You can't tell from the outside whether it formed from 2 black holes, or 3, or 100. You can't even tell what kind of stars it once was. Black holes do not carry names or scars. They do not wear their history on their surface. They are defined only by 3 things: mass, spin, and electric charge. That's all. It's called the no-hair theorem, a poetic way of saying black holes have no extra details, no rough edges, no identifying features. They are pure geometry, simple, elegant, forgetful. But the universe does not forget. Those gravitational waves, the ones that reached us, hold the clues to everything that came before. Even if the black hole is sad to source, the space around it carries the memory. This is the quiet paradox of black holes. They erase their past, but their motion tells us the whole story. And now, as we rest in the stillness after the merger, let's take a breath. Feel what it's like to be in the presence of something complete. No burning, no collapsing, no circling, just still. The gravitational waves are gone. The bell has stopped ringing. Space is smooth again. And the black hole, whatever it once was, now simply is. It sits at the center of curved space, pressing into the fabric like a thumbprint into soft clay. It pulls, not hungrily, but inevitably. Anything that drifts too close will fall in. Not because the black hole chooses, but because the path was already drawn. It doesn't chase, it doesn't judge. It only accepts. But not everything falls in. Some matter, gas and dust swirling nearby, may orbit for a long time. It may glow, heat up, radiate X-rays as it spins closer. And in that light, we sometimes glimpse the black hole's outline, its silhouette, a ring of brightness surrounding a center of darkness. That ring is not the black hole itself. It's the last light we see before gravity bends it out of reach. The black hole remains hidden, even in its moment of quiet power. So tonight, you lie beside the silence of that storm. Not the crash, not the spiral, but the stillness that comes after. It's not emptiness, it's fullness. A quiet that holds weight, a hush that holds memory, a darkness that contains. And maybe, as you drift off to sleep, you can imagine yourself hovering there near the event horizon, watching the soft curves of space slowly settle. No sound, no fear, just gravity doing what it always does, holding, shaping, waiting. But before this black hole ever formed, there were hints. Before it became quiet, it lived as light, as heat, as a star. Can we see the black hole now? Not directly, but we can find its shadow. Let's look for it next. You followed the story this far. A star lived. It collapsed. It became something strange. A black hole, silent and heavy. Now your next question arises. Quiet but clear. Can you see it? The answer, like many answers in the universe, is simple and mysterious at the same time. No, you cannot see a black hole directly. But yes, you can see what it does. A black hole gives off no light. It does not glow. It does not reflect. Once something crosses its boundary, the event horizon, it vanishes from view, its light pulled in forever. So, how do we know black holes are really there? Because gravity leaves a trail. It curves paths. It bends light. It changes motion. And in the world of astronomy, those tiny shifts and swirls are how we see the invisible. Imagine walking through a forest. The creature itself is hidden, but you see broken branches, footprints in the soil, a ripple in the undergrowth. You don't need to see it to know it. Pass through. Black holes leave the same kind of marks in the universe around them. One of the earliest signs came from a star named Cygnus X1. Astronomers noticed something odd. A star orbiting GE, nothing. It was moving in a tight, fast path, as if tethered to an invisible weight, but no companion could be seen. Only X-rays poured from that part of the sky. Waves of high-energy light coming from something unseen. What we were watching was a star, orbiting a black hole, and the black hole was feeding. When a black hole is surrounded by gas, that gas doesn't fall straight in. It spirals, drawn by gravity, compressed by friction, heated to millions of degrees. And before it vanishes, it glows. This glowing swirl is called an accretion disk, a final moment of brightness before darkness swallows the light. And while we can't see inside the black hole, we can see this ring of fire just outside it. We can watch it twist, flicker, flare, and black holes do something else that gives them away. They bend light. They don't just pull it in, they curve it around. Light from stars behind the black hole is twisted by its gravity, creating warped halos and strange arcs. This effect is called gravitational lensing, a bending of light paths through spacetime. It's as if the black hole were a magnifying glass made of gravity, distorting everything behind it. Sometimes it creates rings of light, perfect circles formed by bending starlight around the invisible object. We call them Einstein rings, and they are one of the clearest clues that something massive and unseen is present. So no, we can't take a picture of a black hole itself, but we can take a picture of its shadow. And that's exactly what we did. In 201 Horizon Telescope, a global network of radio observatories working together captured the first image of a black hole silhouette. It was in a galaxy called Messier 87, 55 million light-years away. The image showed a ring of glowing light with a dark center. That dark center, it wasn't the black hole exactly, but the shadow of the event horizon, the place where light begins to fall in. It was the absence that revealed the presence. This was not a normal photograph. It didn't use visible light. It didn't happen in a single moment. It took months of data collected from telescopes all over Earth, synchronized to the beat of atomic clocks, and stitched together with careful hands and patient minds. The result was grainy, fuzzy, but it was beautiful. It was proof, not just of the theory, but of the black hole itself. The image went around the world, a dark circle ringed in flame. Not an eye, not a hole, but something deeper, something that said, "Yes, I am here. You cannot see me, but you can see what I do." And maybe that's enough. Seeing a black hole is like seeing wind in the trees. You don't see the wind itself, but you see the sway, the rustle, the dance of leaves. Black holes sway stars. They rustle light. They bend time. And when we pay close attention, we see them by their influence. Even in our own galaxy, we've done this. At the center of the Milky Way, astronomers have watched stars orbiting a dark, invisible point. One star, called S2, takes 16 years to make a full orbit around something we cannot see. It swings close, then drifts out in a perfect ellipse. We've measured its path, its speed, its acceleration. And from that, we know with certainty there is a black hole there, a heavy one, 4 million times the mass of the sun. And it is dark, utterly, perfectly dark, but it pulls, and that pull is visible. So maybe the lesson is this: not everything real needs to be seen. Some things are known by their effects, by their gravity, by the way they change what surrounds them. Black holes are like this, quiet, invisible, but undeniable. As you rest now, you can imagine that dark circle, ringed in light, pressing into the fabric of space. You won't see it in the sky tonight, but it's there. And in some strange way, it sees you, not with eyes, not with thought, but with gravity, with presence, with the soft, silent influence that only the most powerful things possess. But seeing is just the beginning, because that black hole in the center of the galaxy and others like it don't just exist. They shape, they hold stars together, they anchor entire galaxies. Could it be that black holes are not just endings, but centers? Let's turn there next to the quiet giants at the heart of spiral arms and starlit whirls. There are moments in science that feel like poetry, not just equations and instruments, but something human, something quiet and large. In April 2019, the world was given one of those moments. A blurry ring, a shadow, an image that changed everything. It was the first direct glimpse, not of a black hole itself, but of what it leaves behind its shadow. Not darkness, but the absence of light. A shape drawn not by presence, but by silence. This black hole lives in the galaxy Messier 87, some 50 million light-years away. It's enormous, over 6 billion times the mass of our sun. For decades, astronomers suspected it was there. They saw high-energy jets shooting from the galaxy's core, streams of material that could only be launched by something massive, spinning, and invisible. But it was only with the creation of a planet-sized eye that they could finally look more closely. The Event Horizon Telescope, or EHT, was not one telescope, but many. A network of observatories around the Earth and in Chile, Hawaii, Spain, Antarctica, and more synchronized together, forming one vast instrument. Each site gathered radio waves from the core of M87. Not light you can see, but waves your eyes cannot feel. For 5 nights in April 2017, these telescopes stared into the same point in the sky. And 2 years later, after mountains of data and oceans of patience, they gave us a picture. It wasn't sharp, it wasn't colorful, it was soft, amber-hued, a ring of fire around a quiet center. The world paused to look at it, and for the first time, we didn't just believe in black holes, we saw the space around one. But what were we really? Looking at not the black hole itself, because no light escapes from it. What we saw was the photon ring, light trapped in near orbit, circling the black hole many times before flying outward toward us. The glowing ring forms because matter near the black hole heats up as it falls inward, creating a halo of radiation. Some of this light bends around the black hole before making its way to us, and in the middle, a circle of darkness. That's the shadow. It isn't a shadow in the traditional sense. No object is blocking the light. Instead, it's the silhouette of a place where light cannot return, an echo of the event horizon. What made this image so special wasn't just the science, it was the shape. A nearly perfect ring exactly as predicted by general relativity. Einstein's equations, written over 100 years earlier, had painted this picture in math, and now we saw it in space. The theory had spoken and the universe had nodded. There's something haunting about the image. You stare into it and it stares back, not with menace, not with eyes, but with a kind of still presence. It is not a thing, it is a place where gravity is so strong that time slows, light bends, and the future is sealed. And yet, around that place, so much motion, gas swirling at nearly the speed of light, matter heating to billions of degrees, photons dancing on curved paths. It's a paradox. Stillness inside, fury outside, a glowing crown surrounding a perfectly black heart. What the EHT captured wasn't just an image. It was a confirmation that the universe behaves as we thought it would under extreme gravity. It was a picture of a principle, a diagram made real. And yet, it was also deeply personal, because we didn't build the EHT just to test theories. We built it because we wanted to see, to know, to look into the heart of gravity and say, there it is, I see you. And something remarkable happened when that image was released. People around the world paused, not just scientists, not just astronomers, everyone. They looked at that fuzzy ring and felt something ancient stir, a sense of scale, of wonder, of science. Because even blurry, the image told a story that in the vastness of space there are places where light ends, where time folds, where matter surrenders to gravity, and we can still find them. Perhaps the most poetic part of it all was how long the light had traveled. The radio waves that made that image left M87 over 50 million years ago. They crossed intergalactic space, passed by distant stars, floated quietly through cosmic dust, and were finally captured by machines on mountain peaks and frozen plains, all so we could hold a shadow in our hands. Even now, the EHT continues its work. It has turned its attention to the black hole at the center of our own galaxy. Sagittarius, a smaller than M87's black hole, but closer, quieter, shrouded by gas. That image will come and it will show another shadow, another ransom, another ring, another place where light ends. So tonight, as you lie still, imagine that ring, that fiery halo in the blackness, orbiting an absence, glowing from matter, that did not make it in. It is not a monster. It is not a destroyer. It is the end of falling, the edge of visibility, a quiet boundary where space folds too tightly to escape. And in seeing it, we don't just observe the universe, we join it. Because in every light wave, there is history. In every shadow, a shape. In every ripple of space, a message. And that message burned into the light that made its way to Earth, whispered, even the invisible can be revealed. But that black hole, that massive anchor in M87, isn't alone. Many galaxies hold one at their core, even our own. Why? Why do black holes live at the hearts of galaxies? Are they the end or the beginning? Let's go there, next to the spiral arms and glowing stars, to the silent centers that hold it all together. Galaxies spin, that much you know. Spiral arms unfurl like ribbons in space. Stars twirl in elegant sweeps, and clouds of gas drift gently in their orbits. From afar, a galaxy looks like a swirl of starlight, a pinwheel of glowing dust and gravity. But if you could fly toward the center, past the arms, past the stars, into the crowded core, you would find something strange. Not a bright beacon, not a cluster of stars, but silence, stillness. You would find a black hole, not just in our galaxy, but in almost every large galaxy we've studied. Elliptical, spiral, lenticular. Each one, it seems, carries a black hole. At its heart, a silent giant spinning, waiting, holding. These are not the same as the smaller black holes born from dying stars. They are supermassive, millions or even billions of times heavier than the sun. And yet, they take up very little space. They're compact, like all black holes, their gravity folded into a single invisible point. You might think something that massive would tear everything apart, but it doesn't. It organizes. It helps shape the galaxy around it, not by pushing, not by force, but by existing, by pulling space into its rhythm, by anchoring motion with its weight, like the hub of a wheel, or the still center of a turning dance. Let's come closer to home. At the center of the Milky Way, hidden behind clouds of gas and dust, there's a black hole called Sagittarius A. You can't see it in visible light, but radio telescopes, infrared instruments, and years of observation have revealed its presence is not just a guess. We've watched stars orbit it. One in particular, named S2, follows a long oval path that takes it closer to the black hole than Pluto is to the Sun. And when it swings in near the black hole, it moves us to a speed no planet could match, faster than any spacecraft, faster than logic expects, unless something enormous is pulling it. That something is Sagittarius A, about 4 million times the mass of our Sun, folded into a region no larger than a star. But it's quiet, very quiet. It's not swallowing stars. It's not glowing with X-rays or surrounded by a raging disk of fire. It just sits, not asleep, but still at rest, unless something falls in. And maybe that's the most surprising thing about supermassive black holes. They aren't always active. They don't always feed. They can wait for eons. In some galaxies, like M87, the central black hole is busy pulling in matter, spinning it into jets that stretch for thousands of light years. In others, like our own, the black hole is dormant, like a fireplace where the last ember still glows beneath the ashes. But even when quiet, it holds everything around it in place. You might wonder which came first, Did galaxies form around black holes? Or did black holes form within galaxies? Scientists aren't entirely sure. It's still a question that hums at the edge of our understanding. Some evidence suggests the two grow together, that the mass of a galaxy's central black hole is closely tied to the mass of the galaxy's bulge. It's as if the black hole and its galaxy have been having a conversation since the very beginning, a mutual shaping, not cause, not effect, but companionship. And here's something even stranger. Some of these black holes formed when the universe was still young, less than 1 billion years old. We've seen quasars, incredibly bright, active black holes shining at the edges of the observable cosmos. They shouldn't be that big so early, and yet they are, which means black holes may not just be the end of stars, but part of the beginning of galaxies. Maybe they helped galaxies form, or maybe they grew quickly inside them, feeding on early clouds of gas and matter. The truth may be both, or something we haven't yet thought to ask. But what we know with growing certainty is that these black holes shape their homes. They send out winds, jets, radiation. They help regulate star formation. They balance the flow of gas. Too much activity, and the black hole sends out waves of energy that push gas away, slowing down the birth of new stars. Too little, and the galaxy may grow cold and dim. It's a quiet gravitational balance, one that lasts billions of years. Tonight, as you rest beneath the slow swirl of the Milky Way, know that there is a black hole spinning at the center. You won't feel it, won't see it, but it holds everything and in place, not with violence, but with patience. It is not eating your galaxy, it is anchoring it. It keeps the spiral arms from flying apart. It gathers stars into orbits. It waits, and in that waiting, it shapes everything. It may sound strange that something invisible, something that seems to erase light, could also be the quiet architect of so much beauty. But that's the paradox of black holes. They are both destroyers and creators, both emptiness and structure. They teach us that not everything strong must be loud, that stillness can be powerful, that gravity alone can build wonders. So when you look at a galaxy in a photograph, its arms stretched like stardust across space, remember the center. Remember the silence. Remember the black hole you cannot see. It does not shine, but without it, the stars would drift, the shape would fade, of the galaxy would lose its form. That silence is structure. And perhaps you're wondering now, if black holes grow so large, so quietly, and live so long at the centers of galaxies, what happens when two galaxies meet? Do their black holes meet too? Do they dance? Let's drift into that question next, and watch the slow spiral of inevitable union. In the quiet of space, nothing seems to rush. Stars turn on their axes. Galaxies stretch across the void. Black holes drift like shadows. Everything moves, but it moves in science with the patience of time itself. And yet, even Soundtown has a direction. Even stillness can lean towards something. This is the story of black holes that do not remain alone. Most black holes begin in solitude. Born from collapsing stars, they sit in the dark, pulling gently on whatever comes near. But some, especially the giants, the ones at the centers of galaxies, are not meant to remain isolated forever. Because galaxies move, they orbit, they sway, they drift, and sometimes they collide. You might imagine galaxies crashing together like cars on a highway, but that's not quite right. Galaxies are made mostly of space. Billions of stars, yes, but each one is distant from its neighbors. So when two galaxies merge, it's not a smash. It's a slow dance, a weaving of stars and dust, a pulling of arms, a bending of motion. From afar, it's beautiful. A spiral becoming tangled, a trail of stars thrown outward like glitter. And at the center of each galaxy, a black hole. When galaxies merge, these central black holes begin to move toward one another. Not quickly, not in a straight line, but through gravity's whisper, they begin to drift closer. At first, they are far apart to tens of thousands of light years. But as stars swirl and settle, as orbits shift, the black holes slowly find each other. They are heavy, they are anchored, but the galaxy around them is changing. Like ships caught in a rising tide, they're drawn inward by the movement of everything else. It takes time, millions, sometimes billions of years, for them to get close. Enough to feel each other directly. But once they do, the spiral begins. This spiral is not dramatic, it's subtle. A slow tightening, a deepening pull. It's like two dancers on opposite ends of a quiet stage, moving slowly inward with each graceful turn. At first, the black holes are surrounded by stars, and those stars help carry away energy, smoothing the orbit, bringing the pair closer. Later, as they grow nearer, they begin to send out gravitational waves. These waves take energy away, letting the black holes spiral inward faster until finally they are close enough to merge. This entire process, from the first drift to the final embrace, can take longer than the age of our species. And yet, it happens all across the universe. Even now, as you breathe in this moment, somewhere two galaxies are merging, and at their hearts, two black holes are quietly beginning their dance. But why do they merge? Why not just orbit each other forever? It comes down to energy. Every orbit carries motion, and motion means energy. To merge, that energy must go somewhere. At first, it's carried away by nearby stars and gas. Tiny gravitational nudges like friction in space. Later, gravitational waves carry away the rest. Ripples in spacetime that stretch outward from their circling forms. As energy leaves, the orbit tightens. As the orbit tightens, the black holes come closer. And when they're close enough, gravity takes over completely. The spiral becomes a fall. The fall becomes a fusion. You could imagine it like two whirlpools in water, separate at first, then pulled together by the currents they create. Eventually, they swirl into one, stronger, deeper, unified. These mergers aren't just rare accidents, they're expected. We think they happen often in the life of the cosmos, and each time a bigger black hole is born. This is how supermassive black holes may grow, not just by feeding, but by merging. One becomes two, two become one. A cosmic cycle, quiet but immense. And so we look for signs, signs that galaxies are merging. Signs that black holes are on their way to each other. Sometimes we find two galactic cores close together, each flickering with X-rays, both showing signs of active black holes. Other times we find galaxies with strange shapes, long tidal tails of stars pulled outward like ribbon. And in the years ahead, with better telescopes and new instruments, we may catch more of these black hole pairs in the middle of their slow motion union. Maybe someday We'll even catch the moment itself, the last spiral, the final wave. But even if we don't see it, we'll hear it. Gravitational waves from black hole mergers travel across the universe. Some have already reached us. More are on the way. Each wave tells us that somewhere gravity succeeded, that two became one, that the silence between galaxies is not empty but full of motion. So tonight, imagine two black holes, one born from a spiral galaxy, one from a different cluster of stars. They drifted for eons. They circled in silence. Now they move together, invisible to the eye, but impossible to stop. You don't need to rush. They don't. Their spiral takes its time, but its end is inevitable. And when it comes, it will shape space itself. And here's something to wonder. As they merge, as their horizons touch, what happens to what's inside? What happens to the stars they once consumed, the particles, the photons, the pieces of everything? Does a black hole ever reveal what it has taken in, or does it forget? Let's float toward that mystery next, into the heart of a question even. Scientists still can't quite answer what happens inside. There are questions science can approach, measure, observe, test. And then there are questions that hang like stars beyond reach, and visible but distant, real but wrapped in mystery. What happens inside a black hole is one of those questions. A whisper in the fabric of physics. A boundary we know is there but cannot cross. Not even in imagination, without the map falling apart. Still tonight, we drift closer. You remember the event horizon, the surface of no return. It's not a wall, not a shell, just a region in space where escape becomes impossible. If light crosses it, it cannot return. If time crosses it, it bends inward. From the outside, it looks like nothing happens. An object falling toward a black hole appears to slow down. This light stretches redder, weaker, fainter, until it fades completely. To a distant observer, the fall never ends. It just slows, freezes, disappears. But from the falling object's point of view, the story is very different. If you fell into a black hole, you wouldn't feel anything unusual as you pass the horizon. There's no sudden change, no flash or bang, just an invisible threshold. You drift through it without resistance. But from that moment on, there's no turning back. Space is so curved, so deeply bent, that every possible path leads inward. You cannot turn around. You cannot slow down. You are moving toward the center, always, inevitably. That center is called the singularity, not a place, not in the way we think of places. It's a point where density becomes infinite, where the math that guides our physics, our rules, our models breaks, or time collapses. Space becomes undefined. It's not that we've hit a wall, it's that the road ends and the map folds in on itself. We don't know what happens there. Not yet. Maybe not ever. Some theories suggest the laws of quantum mechanics, the rules that govern the tiniest particles, might soften the singularity. That what we call a point might be something else, a structure, a region, something still mysterious, but not infinite. Others believe that new physics, still undiscovered, will one day explain the inside of a black hole. That general relativity, Einstein's theory, works beautifully until this moment, and then hands the mystery over to something deeper. But until that day, we can only describe what we know. And what we know is this. Once you cross the event horizon, Your fate is sealed. You cannot communicate out. You cannot stop your fall. And time from your point of view marches on. Here's something even stranger. Inside the black hole, space and time seem to switch roles. Time pulls you inward like gravity. You don't fall through space. You fall into the future. And the future, in this case, ends at the singularity. No matter what you do, no matter how you twist or turn, it is the future that draws you there. And so your path is not just physical, yet it's temporal. You're not just moving through space. You're moving through an inescapable moment. So what happens to the things that fall? In a planet, a beam of light, a spacecraft, a single particle, where does it go? Is it destroyed, compressed, stored? This is where physics begins to argue with itself. You see, quantum mechanics insists that information cannot be lost. If something exists, its state, its spin, its energy, those details can be transformed, scattered, reorganized, but never erased. Black holes, on the other hand, seem to destroy information completely. Once something crosses the horizon, all details vanish. Only mass, spin, and charge remain. Everything else, the story of the thing, is gone. This contradiction is called the information paradox, and it's one of the great puzzles of modern physics. Some believe the information is stored on the surface of the event horizon, like a cosmic hard drive, encoding every detail of what has fallen in. Others propose that information escapes slowly as the black hole evaporates, a process known as Hawking radiation. Still others think our entire understanding needs to evolve, that space and time themselves are made of something deeper, a network of relationships, a quantum fabric that we've only just begun to glimpse. Whatever the truth, black holes challenge us. They force us to confront the limits of what we know and how we know it. They are not just objects, they are edges. Edges of physics, edges of thought for two edges of understanding. But maybe that's what makes them so powerful, not just their gravity, but their mystery. They remind us that the universe doesn't owe us answers, that some truths are wrapped in deeper truths, that we can come close and still not see the center. So, tonight, as your breath slows and your thoughts drift inward, imagine the inside of a black hole, not as destruction, but as depth, not as darkness, but as a question, a place where the rules dissolve, where motion becomes time, where endings are beginnings folded in upon themselves. You cannot go there, you cannot come back, but still it exists. Scattered across the night sky is enough to stir wonder. It means the universe has corners that remain untouched by certainty. It means we still have mysteries to fall into. But one more question waits. If black holes take in and hold so much, do they ever let anything go? Do they grow forever? Or do they, to one day, come to an end? Let's float gently there next to the slowest, quietest loss imaginable, to the final breath of a black hole. Black holes grow. That much is certain. They feed on stars, on gas clouds, on entire companions if they drift too near. And when black holes merge, they don't cancel each other out. They add up. They become something larger, heavier, deeper. Growth is in their nature. But how much can they grow? Is there a limit? A point where the black hole says, that's enough? Or could it keep swallowing forever, becoming larger than galaxies, larger than light, a kind of endless sink at the center of reality? To answer that, we drift into the long life of a black hole. We watch it feed, we watch it wait, we watch it change. Growth begins small. A black hole born from a collapsing star might be only a few times more massive than our sun. By gas can begin to accrete, to pull in matter slowly and steadily. This process isn't wild. Matter doesn't just fall straight in. It spirals, forming a glowing disk. It heats up, radiates X-rays, shines with energy before it disappears. This glow is how we find black holes in distant galaxies, not from the hole, but from the feast. There's a limit, though, to how fast this feeding can happen. If a black hole pulls in matter too quickly, the radiation from the disk pushes back, blowing some of the gas away. This balance is called the Eddington limit, a kind of natural speed cap on black hole growth. It doesn't stop the growth, but it slows it. And yet, over millions of years, even slow feeding adds up. Then there are mergers. When two black holes spiral together, they don't lose mass, they combine. A 30 solar mass black hole and a 40 solar mass black hole might become a single 68 solar mass black hole with a few solar masses turned into gravitational waves. It's not just addition, it's transformation. And these mergers can build up over time, especially in the centers of galaxies where black holes are common and gravity brings them together. This is how we think supermassive black holes formed. Not all at once, but step by step, star by star, merger by merger. Now, some are billions of times more massive than our sun. Quiet giants holding whole galaxies in orbit, heavy beyond comprehension, yet invisible to the eye. But even supermassive black holes do not grow forever. Eventually, they run out of fuel, the gas is gone, the stars are stable, other black holes are too far away, and so they rest. There are dormant black holes scattered throughout the cosmos. They've eaten what they could, and now they wait there. Not dead, just inactive, still capable, but with nothing near enough to draw in. It may take millions of years for something to wander close. Another star, another cloud, another black hole. And when it does, the quiet will break again, just for a moment, before the silence returns. But there's another way black holes change over time. Not through growth, through loss, a whisper, a fade. This idea came from Stephen Hawking, a scientist who saw something others missed. He suggested that black holes aren't entirely black, that they give off something, tiny particles, at the edge of the event horizon. This process, now called Hawking radiation, allows black holes to slowly leak energy, not in streams, not in bursts, in the slowest possible trickle, a soft, near-eternal breath of energy back into the universe. The smaller the black hole, the faster it radiates. The bigger it is, the slower the leak. A black hole the size of a mountain might vanish in a flash, in just a blink of cosmic time. But a supermassive black hole, it could take longer than the current age of the universe to evaporate even a little. Still, Hawking's idea was profound. It told us that black holes might not last forever, that even the darkest places fade with time. So we arrive at an answer, not simple, but quiet. Black holes grow, they merge, they feed, but they also wait. And in the farthest stretches of time, they fade. Not from explosion, not from decay, but from a long, slow release of quantum breath into the cold. Imagine it trillions of years from now, when stars have burned out and galaxies are dark. Black holes remain silent, patient, last, and then even they begin to go, one by one, a whisper at a time. They release their heat, their curvature, their story, until nothing remains but radiation. And even that drifts. It is the softest kind of ending. Not destruction, but return. Black holes do not rage at the end of time. They exhale and space becomes still. So yes, they stop growing. Not because they choose to, but because the universe becomes quiet. No more stars to eat, no more gas to pull, no more black holes to meet. Just time and silence, and the final warmth of a shadow letting go. And what happens after that? If black holes fade and matter is gone, what is left? Only space, only the memory of what once was. Or is there something deeper woven into the fabric of the cosmos? Let's drift there next to the waves that continue on even after the shadows fade. To the echoes in the cosmic sea, imagine a wave, not of water, not of sound, but a wave in the very fabric of space. It doesn't shimmer, it doesn't shine. It moves silently, stretching and compressing everything it touches. Just a little, just enough. It travels not through space, but as space, carrying with it a story, an echo, a memory. These are gravitational waves. They come from motion, from mass, from gravity in its most dramatic forms. When two black holes spiral toward each other, they send out ripples, not in light, but in the curvature of the universe itself. And those ripples travel outward forever. They pass through galaxies, through clusters, through light years of silence, and some of them reach us. We first caught one in 2015, a brief signal, a soft chirp in the arms of twin instruments called LIGO. Two black holes had collided over 1 billion years ago. The waves they sent finally arrived, and so faint, so subtle, that they shifted the detectors by less than the width of a proton. And yet we felt it, not with our skin, not with our eyes, but with the tools of listening. The patient machines that stretch their arms across Earth to catch ripples from the stars. Since then, we've heard many more, each one a story. Two black holes merging, or neutron stars colliding, or something stranger still. Every signal is different, a unique fingerprint in time, and the universe, it seems, is full of these echoes. What's remarkable is how long they last, how far they travel, how gently they move. Gravitational waves don't scatter like light. They don't fade as quickly. They move cleanly through the cosmos, passing through gas, dust, even you. Right now, this very moment, you are being stretched and compressed by the waves older than Earth itself. You don't notice. They are too faint, but they're there always. And what do they carry? Not matter, not energy in the usual sense. They carry information, a record of motion, of mass, of change. When we detect them, we're not just hearing the past, we're feeling it. A gravitational wave is a memory that space has chosen to keep. It's like listening to a bell that was struck long ago. The sound is gone, but the vibration continues, a soft hum in the background of the universe. These waves are ancient. Some were born before our sun existed, before Earth cooled, before any mind ever opened to wonder. And yet, they still arrive, quiet. True, you might ask, if black holes eventually vanish, if stars fade, if everything grows cold, do the waves stop too? Not really. Gravitational waves are not tied to heat. They do not burn. They do not need fuel. Once created, they travel on uninterrupted. They grow fainter as they spread, but they do not vanish. In the long dark future of the cosmos, after the last light is gone, gravitational waves may still ripple outward, carrying memories long after the sources are gone.